M30 in the AM. Currently, we're going to look for a high of 3 degrees today, this afternoon. It's going to be lovely out there. Be careful on the roads. It could get icy. Right now, we are continuing on with equilibrium formation. And yesterday, we took a look at this graph, forming it today, the second side of that sheet. Look at this reaction. Okay. I'm recording. Thought I'd put the weather on. This is not live, so if you watch this. Yeah, well, it's clear on, yeah. All kinds of things. I know. So somebody would watch this, catch up on the current events and stuff like this. They shot the balloon down over top of the United States. Yeah. Okay. So here's what we have for this reaction. Now, I'm going to put the balance numbers on top of the chart. I'll show you why. One for the N2, I'm going to see this. Science appreciates me. Anyways, that's my kind of blessing. Sure, rubbish. Now I'm putting the balance numbers, I'm putting a thick line there to separate the reactants and products. I'd advise you to do the same. Then we're going to talk about this, see how it works. And here's what I want you to know. Okay. So it takes one of these and 3 H2s. 1 N2 to 3 H2s. Make this, right? It's a 1 to 3 ratio. You make NH3, it's called ammonia. It's 2 of those. Everything has a different balance number, and I wanted to use a reaction. The math isn't too tough. You need a calculator. But here's what I'm going to see. The first one is completely filled up from 0 to 1. But let's just analyze this and see how the ratio is. When this goes down by decimal 1, right? I'll put the minus 0.1. It's supposed to be in a 1 to 3 ratio with hydrogen, right? It doesn't go down by 3 times that much. Yes, it does. Minus 0.3. 1 minus decimal 2. If the left side is going down, the reaction, that must mean products are being produced. So this is going up, and it's a 1 to 2 ratio between N2 and N3. So then it is going up by 0.2. So the arithmetic is kind of easy. We're going to use that same logic now to do the next. Now, I won't rewrite the numbers, but I think 0.9 to 0.8 is also minus decimal 1, right? So it should work in the same ratio here. If you do the arithmetic, 2 times as much should go down. So if you want to calculate it, go ahead. But what's 0.7 minus the decimal 3? Blurred it out. Yeah. But we're all learning together. 0.4. And if that side goes down by decimal 1 for the N2, I like comparing 1 to 2, 1 to 3, so I don't use the H2. 3. Anyway, this goes up by decimals, so we're going to decimal 4. Okay, finally, something different. So I will jot in this, 0.8 to 0.75. The difference is 0.5, decimal 0. This goes down by 0.05. That goes down by 0.5. And we know that the N2 to H2 ratio is 1 to 3. What does that go down by? Ask yourself that. 5 times 3 is 15, right? So decimal 15. Now I'm squeezing this in here just because that's my thought process. Absolutely need those little arrows and the subtractions and no, but I'm trying to teach you guys. Hey, this made sense, right? 40 minus 15 is 25. So that's the best one. And then this one, a 1 to 2, or 1, yeah, 1 to 2 ratio. M2 goes down by 0.5. This goes up on the opposite side by 0.10. I say 10. Using that logic, can you guys fill in the rest of that chart? Now, the numbers are different. It's 75 to 72. It's 0.3. I'll pause the recording. You guys fill that out? Okay, going over the thought process here, and I'll use a different thought. 75 to 72 is down over 3. This goes down by 3, and H2 is on the same side, but it's 3 times as much to decrease on, right? So 3 times 3 is 9. So 0.9 down. I'm subtracting. Okay? 25 minus 9. Yes. 16. 0.1. And I put that dividing line here to remind me of that's dividing the product and the reaction. So one side goes down, the other side goes up, and it's a 1 to 2 ratio between N2 and NH3. So that's twice as much, so 0.6. So 50 plus 0.6, 6. Does that make sense? Double check for the thought process here. 72 down to 70 is 0.2. Down by 2. That goes down by 2. 3 times that is 6. What I'm writing there with arrows is my thought. Whether you write it out or not. 16 minus 6 is 10. This side is going up twice as much, so 2 times 2 is 4. I'm adding 56 and 4, so 60, 0.6. Now, what do you notice about the last line? There's no change. So if there's no change here, it's all going to be the same. So I'm going to put in the 10 again. No change. 7. Okay. Now there's some thought questions out here. Yeah, before I move on though, we get how you use the balance numbers only for the change, not the actual ending amounts, right? Pluses and minuses. One side's going down, the other side goes up. Obviously, things get more complex. Fill in the question marks. I get that. I don't even think so. When was equilibrium established? When is the first time we had the amount that stayed the same? Yeah, AM we're going to see that. So it's at 5 seconds. Don't say 6 seconds because it's already established. 5.0 seconds. That's what I really want to see. What is the thing? I said this at the start of class. What is equal at equilibrium? Not the amounts, not the changes necessarily. What is equal at equilibrium? Yeah, forward and reverse reaction. Not the same. That means as much product is being made as reactants is being made. Like the left reaction and the right reaction are both going at the same time. It's like that snowball fight idea. Just as many snowballs are being thrown north as they are south. Right? So what is equal at equilibrium? The forward and reverse reaction. Squeeze that in. Okay. find something out to you guys in the next minute or so. Okay, before we get started on the lab handout, a few things to remind you. Dynamic means moving, right? Maybe you didn't. Dynamic equilibrium. When reversible reactions are placed in a closed system, the macroscopic, not micro, big observable properties of the system become constant. So that was the color of the red in the reaction that we saw first day or second day. This is when the system is at equilibrium, no changes. It's noticeable. Equilibrium is dynamic because the forward and reverse reactions occur with no net change occurring in the system. You've got to get that in your head. What's equilibrium? Forward and reverse reaction lines. Now, you jot this down at the top of your page. You don't have to do these notes or whatever, but at the top of this page. Conditions. Closed system and reversible reaction. So, for conditions for equilibrium, if you want to add something, this is what I want you to get out. Okay, give it a second. Recording. Okay. When I say reactions must be reversible, I think we're getting the idea. Right? Every reaction is the closed system. That's dependent on the actual state of matter. If you have a gas, that's going to be different than a liquid or a solid. So, in a test tube or a beaker, open test tube or an open beaker, if I have a gas present, that's not a closed system. But if it's strictly liquids, which I'm holding up in test tube right now, this is a closed system. I put the solid sodium chloride in here, the water is the other. That's a closed system. Makes sense? Gases escape. So what you're producing in gas, this would not be. You know, that builds up pressure in one other factors. We'll look at later. So what you got to be careful about is there a gas present? Okay, I'm not going to go through that. It's basically a rehash of what we already talked about. But what I am going to do is your handout. Get your lab sheet. We'll talk about this, and then we're going to observe some things that won't appear on the video because we don't want to show the screen. There's something called the Chateliers principle. So obviously a French view. And as principle states, if an equilibrium system is subjected to stress, the system will react to remove stress. Sort of sounds like Newton's one of Newton's laws, the third one, right? Equal and opposite. But some of you, it doesn't matter how. To remove a stress, the system can only do one of two things. Form more products, use enough reactants, or reverse the reaction, form more reactants, use enough products. So it either shifts to the left momentarily or to the right momentarily, or the reverse. This experiment on several equilibrium systems, then put different stresses on the system. See how it reacts. We're going to be able to make predictions. So the first one I'm going to do, and I have to do this because it involves hydrochloric acid as strong and right. I've just rewritten what's up there, but I did color it. So I might have noticed and mentioned I put salt, sodium chloride, into this water. Right? So I have a really saturated solution. You see the table salt sitting at the bottom. That means saturated means nothing more than dissolving, no more salt. So here's what we're going to do. Predict what the effect of increasing the chloride is going to do. Now let's just think about this before, and this is the first time you maybe thought of it. So as you new to you, we'll do it as a group. And, well, let's just think this through. Right now, we have a system. Sodium chloride solid is sitting at the bottom of the test. Sodium chloride back. And every second, there's some sodiums and chlorides that go into solution. But at the same time, you have an Na and a Cl that bump into each other and fall down. So really, if I look at this a minute later, we have a salt at the bottom that doesn't look any different. What that cause of that also? But because if I give this time, it'll settle out. Just because of now this stuff I'm not worried about because it's sodium chloride. It's sodium chloride. No. This is still, I'm going to leave it for a minute. And it should settle out. This stuff still has these salts in it. We'll see if it clears up in a second. But our question was, what happens if we increase the amount of Cl? Right now it's at a balance in that forward and reverse reaction rates are the same. If all of a sudden I increase this stuff, I have too much of this, how does the system, because it has to do something to get rid of the excess Cl at the moment? What's the only way that it uses up Cl? Forward or reverse? Reverse. It's got to go to use up the extra. It's got to go this way more than that. Now, let's talk about this in a second. When it does that, that means it should make more sodium chloride solvent, the salt. You should see some particles. Now, the way we're going to add the Cl, though, is you can't just get a jar of Cl ions, like chloride ions. So we're going to add it from HCl, hydrochloric acid. And it's going to be really strong. This is why I'm not going to do it. Now, I wear glasses, so I don't need safety. When I do that, it should use up so I add the extra stuff in the form of HCl acid. Then it's going to shift this way more than shift reverse. It'll also use up the sodium, though. The only way to use up excess Cl, chloride, use up sodium ions. So it's going to deplete the sodiums that are floating in solution. Make more sodium chloride salt. Pause the video. So initially we changed, this is the order I kind of would write. Initial change, add Cl. You think, how does the system use up that? How does it bring it back down? Screwed up the equilibrium. Well, the way it'll bring it back down is to shift to the left momentarily to use up the excess Cl negative. And it should make more sodium chloride. So, you guys jot that prediction down. Just on your sheet. And then we'll observe and see what happens. So for the acid-base indicator equilibrium, I want you to emphasize it's a double arrow. And here's, we don't know a lot about acids yet, but acids are a source of H+. This is the indicator, gives off, reacts to form H+, and then In negative, this blue indicator. The yellow form of it, and it has the H attached, it's yellow. When it releases the H, it's blue. The other thing I want you to jot down on here is, because we don't know a lot about acids and bases yet, is that a base, we're going to use sodium hydroxide, removes H+. Bases are the opposite of acids. By the way, you don't hear about bases much in movies. But they can be equally as destructive or corrosive. adding H plus, and how is it going to screw up this equilibrium? Well, we'll find all blue. So we're going to use this bromothymol. Here's what's going to happen. By the way, IN for indicator is just, it's a really big molecule. I didn't want to write out the whole bromothymol. I'll get to that now. So if I add H plus to this system, let's think about this, predict. If I add H plus to this, all of a sudden it has extra H plus. Which way does the reaction have to go, left or right, to get rid of the extra H plus? It has to go down. So we should see, so if I add H plus, we should see something like yellow, right? Then, if I add a chemical, or it's called a base, it gets rid of, and it's turned yellow. If I get rid of the H plus, how's the system going to shift to replace the lost H plus, which is the only way that makes H plus? This way. It'll momentarily shift more to the right than the left, and it should turn blue. You should see that. So that's what we're going to hopefully see, but it's the logic behind it. And I've got this down, basically what you were just saying, but I haven't. When H plus is added, the reaction shifts left to get rid of the excess. As a result, HIN increases and the indicator negative ion decreases. You will observe yellow. I'm going to pause the video part, but we're going to take a look. So to make your predictions for this, the very first one, so A, right, you're going to add in when heat is added, right? Let's look at this reaction and just see what happens. So write down when heat is added. Okay. Somehow lost the reaction. I'm going to grab the reaction while you guys are. Okay. Now, heat is energy. Let's go through this first one and we'll make a prediction as a group. When heat is added, well, that's heat is part of the reaction. It's energy. You're going to have extra energy. And when it's just like having an extra chemical. It might be easier to think about that. If we had more ingredients, reactants, Cl negatives, how do you get rid of extra Cl negatives? Go to the other side, but explicitly to the right. Shift. Okay. Well, we have extra heat energy. That means you have more fuel to drive the reaction, right? Energy. So the reaction will shift. Which way will the reaction shift? To the right. You guys know from the fill in the blank choices, left or right. And then I'll just finish this real quickly. So that reaction system, we're adding heat, uses excess, and then we'll say heat. And you can see that on the right, products will increase, the blue color will be observed. Okay, add products. So we put heat. Okay, so tomorrow we're going to do those. We'll take some time at the start of the class for you to finish off some predictions.